So today is 21st lecture and we are now discussing a little bit more into the pulse width modulation techniques, its implication on the motor drives, and how do we realize a good PWM for a given motor drive. So these aspects we are looking into. So whatever we have discussed so far, based on that, we have understood that if we have the freedom to make the ratio of switching frequency and fundamental frequency high, let us say more than this number, then it is not advisable to go by the methods where we compute the switching angles within the quarter cycle and then we realize the waveform. This may not be a feasible way because there may be so many angles over here and it may become difficult eventually to solve all the angles and then you store it somewhere and then take it out for realizing the waveform. So one thing you note over here is that if let us say I asked you to generate modulation index say for 0.8. So we are asked to generate output, of course, balanced three-phase output. For this particular modulation index, we need to know the switching angles at least in all the, within one quarter cycle, all the switching angles within this. So much of information is needed if we are trying to figure out what is the voltage that is going to come out from this inverter at this modulation index 0.8, and I'm assuming that V by F is maintained. So telling modulation index is enough to tell what is the frequency. So frequency could be 0.8 times of 50, that means 40 Hertz. This is for a 50 Hertz cycle I'm talking about. Now, when we have such freedom that our system power is not very high, we do not have very high frequency fundamental, then this condition can be met. And then we are trying to look at different way in which we can realize our output voltage in a bit more easier way. So what we have basically, again going back to our SPDT switch and inverter leg. So let's say R phase we are trying to have over here. So output always we are talking about the at point R with respect to O. So with respect to O, this point is plus VDC by 2 and this DC bus is at minus VDC by 2. And we are generating out of this. Now only two possibilities are there for VRO. It could be either plus VDC by 2 or minus VDC by 2. So what we can have, let us say, if we can operate this SPDT switch over here at a much faster rate. So what we can do, we can operate, let's say we can connect it to throw 1 for some duration and then we can connect it to throw 2 for rest of the time. And what we do that, somehow we fix this interval. Let's say this is called TSW. The switching period we are somehow fixing. Here it's not fixed. When we talk about low switching frequency, the same thing is not fixed. Switching angles could appear anywhere within this quarter cycle and so on the other half also. But here we have a more repetitive pattern. So after every TSW there has to be one notch, or within one TSW there has to be one notch. So this pattern is repeating itself several times. Now what is happening that if we have such flexibility and we are able to generate this output voltage, say plus VDC by 2 and minus VDC by 2, and let me call this duration as T on. So T on refers to the time when the top switch is on. This is definition of T on, let us say. And whenever this bottom switch is on, we say that the time period is T off. So we have this arrangement. Now, if we try to compute similar to the DC-DC converter, what is the average VRO generated over here? So what it would be? So what I have here is that plus VDC by 2 is applied for time duration up to T on, and then from T on to TSW we have minus VDC by 2 applied at the pole voltage. So this is what we are generating. Now what is the average value over here for VRO? If I talk about only this switching period. So we can write plus VDC by 2 times of T on plus minus VDC by 2 times of T off, and this whole can be divided by TSW. Correct, right? We are only balancing the volt second, you can say. So whatever positive volt second we have applied and the negative volt second what we have applied divided by the total time period. So that's the voltage we are generating over here on an average. So then average value of voltage can be written as VDC by 2. And if you simplify, keeping in mind that T off is basically TSW minus T on. So we don't have everything as variable. We have at the most two variables in this system, say T on and TSW. And once we fix TSW, by changing T on, we can define what is T off. Am I clear here? Is this statement clear to you?
Yes, sir.
Okay.
Yes,
So
sir.
now if you simplify this equation, what we will find that 2 times of T on by TSW minus 1 is the factor which is getting multiplied with VDC by 2. You understand my point here? Now,
Yes, sir.
if you recall from the DC-DC converter, what this quantity is T on by TSW?
Duty cycle.
Duty ratio.
Duty cycle. Duty ratio we have defined with respect to the top switch only. That is T on by T off. So this is for the top switch. So if this is the duty ratio for top switch, what is the duty ratio for bottom switch?
TSW. Huh?
Yeah, it should be TSW. So if this is duty ratio for top cycle, what is duty ratio for bottom switch? Similar way you can say that T of
Sir, 1 minus T2.
Yes, exactly. So either you can say T off by TSW or you can say 1 minus T on by TSW, and in effect it is 1 minus DT. Correct? So this is how the top and bottom switch duty ratios are related. This is bottom switch. Now we will refer to duty ratio as the duty ratio of top switch only. This will be our reference. Correct. This is for your understanding only. I have derived this expression for bottom switch. But when we say duty ratio, we will invariably referring to the top switch alone. Now I can write this as a simple variable D. And I can write as 2D minus 1. Now, this is what I am having as expression for the average pole voltage when I have a variable which is duty ratio, which means I have the flexibility to turn on and turn off my top switch and bottom switch at my wish. Now, what is the maximum value of duty ratio? What could be the maximum value of duty ratio? 1. The switch may be on for entire TSW. What could be the minimum value of duty ratio?
0.
0. The switch may be off for the entire duration. Correct. Now, for this extreme values of D, what will be the average value of VRO? So let us say VRO maximum could be plus VDC by 2 when we are having D equal to 1. Understanding my point? Or my VRO average could be minimum minus VDC by 2 when my duty ratio is 0. So this scenario is equivalent to we have the switching period, let us say up to this point, and I am keeping my top switch on for the entire duration. So of course the average value obtained over here is plus VDC by 2. And then the second scenario, we have the entire duty cycle, entire switching period, and we are keeping the top switch off, which means bottom switch is on, and so we have the value minus VDC by 2 applied at the pole voltage. So the average value is of course VDC minus VDC by 2. You understand the point? Similarly, we can pick up any value. Let's say if you take, for example, D equals 0.5. What will be the value of this?
0.
0.
0.
Now what it means? Which means that for this switching period, we are applying plus VDC by 2 for half time and minus VDC by 2 for rest of the half time. So whatever you have applied on the positive this portion, you have applied in the negative portion as well. The total time is TSW. So this is half TSW by 2. So what we are basically able to do that with respect to the duty ratio, we are able to generate certain average value for the pole voltage. Now, if you take any value, let us say your D is varying from say D is varying all the way from 0 to 1. Correct? It's linearly varying, let us say. So what will be the response of your average VRO? What will be the response of VRO?
So linearly increasing, starting from minus VDC by 2 to plus VDC.
Yes, exactly. So it will also change from minus VDC by 2 to plus VDC by 2 in that same linear fashion, and exactly at D equal to 0.5, it will be 0 over here. So this will be nature of VRO. Understanding my point? So this is one mechanism through which we are able to generate any VRO on an average basis. See, I'm not saying what is the instantaneous value. I'm talking about the average value of VRO over the switching cycle TSW, over the switching time period TSW. Correct? Instantaneous values are still plus VDC by 2 or minus VDC by 2. These are the instantaneous values. However, on an average, this can be taken as anywhere between minus VDC by 2 to plus VDC by 2. Now, this is the concept we are going to use to realize our next PWM scheme. So what we have basically, when we have this kind of structure, how do we generate a fixed switching time period and the corresponding duty ratio? So again, we go back to our DC motor, or sorry, the DC-DC converter principle. What we had there, basically we are trying to generate some output. Say, because it's only unipolar in the DC, so I will draw only this positive. Say you are having some plus V and 0. This is what you are trying to generate. So how did we do? To fix this, because this is important, the switching period must be fixed if any of these calculations has to go correct. What we did, we had one ramp signal or carrier signal, which is repeating itself every TSW. So say it is changing from all the way from 0 to 1. And what we do, we compare a reference signal, say small m, and small m can have value between 0 and 1, because if it goes below 0, there is no point, there is no comparison happening. So PWM is saturated. And if you go above 1, the same scenario, there is no comparison. So no control over what you are applying. In between this, we have a linear relation between what output voltage we are getting on an average and this reference signal. Understanding my point?
Yes, sir.
So,
Yes.
what we can do, the same principle we can extend, and we can realize, let us say, now we have to realize the output voltage as a sinusoidal waveform. This is what is our target. This is what we are trying to realize. Now, this time period is, let us say, T. So the assumption is that TSW is very, very small compared to T. It's almost incomparable. So ideal situation, if we have to generate this kind of VRO, let us say, under ideal situations, what we should do? We should actually realize each and every point on this waveform. The infinite number of points should be realized on this waveform on average basis to ensure that we are generating this waveform. You understand this point? Am I clear?
Yes, sir.
Yes, sir.
Just one second. Okay, so this is what ideally we should have. But for this ideal scenario, what is the requirement? The requirement is that our switching frequency should be almost infinite. We should be able to realize each and every point. So this actually means that TSW is very, very close to 0. And that is why each and every point we are able to realize. However, that is not possible practically. We know that FSW is finite and we cannot have each and every point realized on the waveform. So what we can do? At least we can pick up few points which we can realize comfortably. Let us say these black dots. Sufficient number of points, let us say 50 or 100, something we are able to generate on this waveform on an average basis. So that is sufficient. It is very, very close to the sinusoidal waveform. Correct or not?
Yes, sir.
So
Yes,
what
sir.
is the actual waveform that is generated? We are basically trying to generate this voltage level. So there is some switching interval involved. Over this TSW we have realized this voltage level. Next, over this interval we have realized this voltage. Next, over this interval we have realized this voltage, and so on. We keep going with several realizations in every interval. So in effect, what we have is that we are realizing this staircase kind of waveform. Understanding my point? So the more number of steps you have in this waveform, the better the waveform will be. Better means it will be closer to this sine wave, which is clearly seen, right? Worst what you may have, let's say, one sample here at the peak. So, and at the negative peak, you may have another sample. This is the worst. Now, anything you do, if you have more number of samples, this would be better than this. You understand my point? So the number of samples is directly relating to the switching frequency. Understanding my point?
Yes, sir.
Yes, sir.
So
Yes, sir.
each and every step is basically giving you how fast you are realizing the average value. So how to achieve that, or how to do that basically, and how to relate your output with something which is called, which can be called as a control variable. So extending the same concept over here, whatever we have done for DC-DC, we can have basically a reference signal which is varying sinusoidally instead of a fixed constant reference signal. So we can have a reference signal like this. Understanding my point? And you compare it with the carrier. Now, in case of DC-DC converter, we have the ramp going between 0 and 1. Whereas here we want to have comparison for a quantity for this reference signal which is having a sinusoidal nature. So maximum values could be between +1 and -1. So obviously we need a bipolar ramp over here. where the value of this ramp will change from -1 to +1. Otherwise, it will not compare in the negative half. Correct? So we should have uniform comparison in all the sectors or in all the sections. So we should have bipolar ramp kind of carrier. Correct? In other words, what we are doing that. Yes. In other words, when we have said that this TSW is very, very small compared to the time period T of the fundamental, we are also saying that the change in our fundamental, let's say this value M, the reference signal, within one ramp cycle or carrier cycle is negligible. The change in M. So what is the meaning that if you, because these are only few cycles what I have drawn over here, let's say you draw 100 cycles or 50 cycles over here, how it will look like on per cycle basis is that you have ramp and your reference signal will be, let's say, almost constant during this cycle. Then in the next cycle, what will happen? It may slightly change. So it may slightly go up. Understanding my point? The other way to ensure this kind of constant nature of the reference signal, we can have sampling for the reference signal. Let's say you sample at every valley. At this point you sample. So what will happen? Whatever value you have, it will be fixed through a sample and hold. Then again, you next point you sample here, it will be held at this point for this entire cycle. Again, next sample you take over here, it will be held at this point. So using a sample and hold kind of circuit, we can have realization of this kind of reference signal. So meaning to say that even if it is changing in between somewhere, it does not matter, right? Only it should not change significantly. If it is changing significantly, that means our realization may be inaccurate. Correct? We are not satisfying this condition. You understand this point or not?
Yes.
Yes.
Clear to everyone?
Yes, sir.
So
Okay. Because sine triangle is anyway simple thing, all of you are experts in that. So I'm only trying to get some insights what we should have in that. Now, when we have said this, so what we are trying to do basically, we are trying to relate our output voltage which we have derived in terms of the duty ratio with the control variable or the reference M. Now when we are saying that M is some sinusoidal quantity, we can write M in this form. Correct? The omega t will decide at what, this omega will decide at what frequency it is going. So this is what our reference signal could be. And this is generally for the DC to AC converter, it's called basically the modulating signal. And this capital M, basically this defines the peak of this modulating signal is always between 0 and 1. And this is here called modulation index. We have seen another modulation index in the low switching frequency case. How this is different or related, we will see shortly. So this is what we are having as the modulating signal and the modulation index, and this is what our average VRO is with respect to our duty ratio. Now we are trying to correlate our reference signal or modulating signal with the VRO. So what we do basically, we again go back to our ramp and the comparison. It's going from -1 to +1. There is, let's say, here is the 0 axis. So let us say our modulating signal is somewhere here because it is m sin omega t. It could be anywhere between +1 and -1. So let's say it is here at some point. Say this value itself is small m. Now what will happen when you apply this kind of reference and carrier and then operate the switch? You will generate a voltage which will be of this nature. So plus VRO up to this point, because whenever M is greater than the, say, carrier, we have VRO equal to plus VDC by 2. Otherwise, we have VRO equal to minus VDC by 2. These are only two options. So simple, like DC converter, DC-DC converter, we know that. So this is what the output waveform will be generated, corresponding to this kind of modulating signal. And we know that this is what we are calling as our duty ratio, the ratio between the T on and the total switching cycle TSW. This is defined as the duty ratio. So we know that this interval, if we scale it with respect to TSW, this is basically D. But anyway, we will do that. VDC by 2 and minus VDC by 2. Now what happens? Let us say if you take this height, this is basically 2 and this height is M over here, and this is the total time period TSW. What we are trying to relate? We are trying to correlate D with the variable M. So you can have again the properties of similar triangle. Let's say I take a triangle ABC over here and say this is DE and this point is F. So because these are all within same parallel lines, so we have triangle ADF is similar to triangle ABC. Isn't it? We have the same angle over here and 90 degrees of course common over there. So similar triangle property we can use and we can understand how this is correlating with that. This point is clear, right? Any confusion in this? So we can relate this height with this and this duration with the total duration, which is TSW. So we can write AF by AC equal to DF by BC. Correct? Any confusion in this? It's correct, right? Ratio of the base equal to ratio of the perpendicular. Fine. Now what is AF basically? AF is the T on duration and AC is the total time period TSW, which is equal to DF. DF is what? This total height will be 1 plus M, the magnitude of this. This is 1 and then plus M. And BC is basically 2 from -1 to +1. So T on by TSW is basically D. So we have D coming equal to as M plus 1 by 2. Understanding my point? Now we can plug in this value of D in the VRO voltage what we had developed earlier, this average voltage, and what we can find VRO average is equal to VDC by 2 times of 2 M plus 1 by 2 minus 1, and which simply comes as M times of VDC by 2, which is the famous expression we know for sine triangle PWM. Isn't it? This is the VRO value we get when we have a modulating signal and we have the DC bus voltage given. Now you can expand the small m in terms of capital M and sine omega t. So it can be written as m times of VDC by 2 sine omega t. Now when m changes between 0 and 1, your VRO can change between plus VDC by 2 and minus VDC by 2. Correct? So these are the limits on the, and you can say average. It's not instantaneous, so I'm putting this bracket VRO average. So these are the extreme values of VRO, what can be realized from this type of comparison, from the reference signal and carrier comparison. You understand the point?
Sir, last point is not clear. MVDC by 2 sine omega t.
What is not clear in that?
Sir, how you write this expression?
This is what we defined our reference signal or modulating signal, right?
Yes, sir.
Yeah, capital M is the modulation index we have said, right?
Yes, sir.
Is this not correct or any problem in this one? Yes or no?
Yes, sir. It's clear now. Yes, sir. Yes, sir. Clear.
So now you see the definition of modulation index getting more clear over here is that you are writing VRO equal to, and again when I'm referring to VRO, this is average. So I'm putting the bracket as well. Capital M VDC by 2 sine omega t. And we are saying that maximum VRO average is plus VDC by 2 or say VDC by 2. So then modulation index is again ratio between what is the maximum voltage, sorry, the actual voltage divided by the maximum VRO. So, okay, let me write in this terms VRO max. This is what the definition we have given for the low switching frequency case as well, right? Correct, right? We had given the maximum,
Yes, sir.
sorry, the actual divided by the maximum. So in case of low switching frequency, the V1 max was 2 VDC by pi. Whereas here we have max as VDC by pi. You see the similarities and differences? So obviously when someone is referring to modulation index, you must need to know which PWM he is referring to. When you say modulation index, first question you need to ask for which PWM. For low switching frequency, the definition of modulation index is this. Say you have 100 volts output generated. You cannot say what is the modulation index unless you know which PWM technique is applied. You are understanding my point here? So one place we have the modulation index with respect to the maximum value, which is plus VDC by 2. Another place we have modulation index in case of low switching frequency, the maximum voltage is 2 VDC by pi. Yes, Deepak?
Sir, sine omega t term, you like m
We are
sine
talking about
MVDC.
magnitude, right?
Okay.
See, these are all sinusoidal quantities. We are
these are all
talking about the
sinusoidal.
amplitude. Correct?
Okay, sir.
So here we have to define which PWM technique you are referring to before saying the modulation index. So few differences which you can correlate from the previous PWM technique to this new PWM technique what we are developing is that the DC bus utilization is different. Here in this case it is only 50%. You cannot have M more than 1 because then you will lose the linearity. The condition is that M should be between, capital M should be between 0 and 1. Otherwise, the reference signal will go beyond this carrier. So what will happen? There is no comparison. Then we don't have any relation between the control signal and the output generated. We can have anything said about the output with respect to the reference only up to this point between plus and minus 1. If you cross that boundary, then we cannot say anything. Understanding my point? So keeping that constraint in mind, we have only this utilization of VDC, sorry, the DC bus voltage. It's only 50%, right? You understanding my point or not?
Yes, sir.
Can you quickly compute how much was here for low switching frequency?
63.
What is the value of 2 by pi?
63.6%.
Should be more actually. Why? Okay, fine. So you clearly see that there is some difference, no? Almost 13% difference if you see with respect to this. So always our reference point should be fixed first while talking about percentage. So with respect to the low switching frequency PWM or square wave, we have 13% reduction in the DC bus utilization. Understanding my point? This is the maximum absolute number. We cannot have AC voltage more than this type of percentage. This is the absolute maximum number. Any other PWM technique we are having that will only reduce this utilization. Understand my point? So yes, we do have some advantage when we are going for this kind of PWM technique, but we are losing also something. So keep these things in mind. Now let us go into three-phase realization of our this new PWM what we have. I am still not calling it the name what you know famously. There is a reason behind that. Let's say I have my three-phase inverter. So three SPDT switches are there. Now, if I have to operate this converter using this new PWM scheme what we are discussing, what we need to have basically, we need to have three modulating signals for the three-phase legs. For operating these three SPDT switches, we should have three different modulating signals. One modulating signal cannot do that job. So we will have, say, MR for this R phase, we will have MY for this Y phase, and MB for the B phase. Now, when we are trying to have balanced three-phase output from this converter, we must have the balanced three-phase relation between these modulating signals, because ultimately VRO, VYO, VBO are proportional to the modulating signals. VDC by 2 is only the constant factor, right? So what we should have, if MR is defined as capital M sine omega t, MY should be capital M sine omega t minus 2 pi by 3. And MB should be M sine omega t plus 2 pi by 3. Understanding my point? These are three-phase balanced modulating signals for controlling each leg of the converter. Similarly, you may have 5-phase, 9-phase, any converter. You can give the appropriate balanced modulating signals and you can generate the correct output. Now, for all this, we should have generally the same carrier for this comparison. Understanding my point? Fine, yes or no?
Yes, sir.
Yes, sir.
So what we have done, we have started from this, the duty ratio expression, and we have gone to realize the output voltage in terms of the modulating signal. Now this I have not stated any phase for this. So generally this relation, what we have written, okay, I think I should write that expression once at least. Yeah, so let me write over here VRO MVDC by 2. This is in general true for every phase. Whether we talk about R, Y or B phase, this is in general true. So what we will have basically, this waveform, carrier waveform, which will be common for all three. So if I plot it over here, say this is the carrier, and okay, I will use a scale from the next time. So today's class we will just see this. This is our carrier, and this is the zero axis, of course. Then let's say we have our modulating signals. These are balanced three-phase modulating signals. So let us say MR is somewhere here. Say MR equal to 0.2. Now MY is somewhere here. Let us say 0.4. So then MB must come. Okay, Y I can draw here, right, with this different color. And B must be then minus 0.6 in order to ensure the balanced three-phase system. And this carrier signal is repeating itself. Now, in response to these reference signals, these three-phase modulating signals, our converter will generate the output, or you can say the gating signals for the IGBTs, which may look like, so up to this point the R phase is high, so there will be gating signal given like this, and then it will go 0. Then for the Y phase, it will be up to this point. So it is high for longer duration than R because the value is also more. And then we have B, which is basically negative. So it will be off for more than off for more duration compared to the on duration. So the on duration will be small and off duration will be more because we are realizing negative voltage for this. If it is 50%, then it will exactly match 50% of the on and off. Now this is what we have for gate for the R, then gate for Y and gate for B. You understand this point? This is how the gating signals will be given for the top IGBT. For bottom, it will be just opposite of that with consideration of dead time and other things. Now, what we observe over here is that the pulse is starting during this and it is ending over here. Again, this Y is also starting over here and ending over here. B is also starting over here and ending over here. The immediate next cycle, when this carrier again starts from here, what will happen? All the three modulating signals are higher than this carrier. So immediately, all three will switch to high. The gating signal will immediately go high for all three. So at this point, what we are seeing, whenever the new cycle for carrier is arriving, there are three switching instants occurring at the same point. Three switchings happening at the same instance. which is basically not a good condition for operating a converter. So converter, what we should have basically, the best scenario is have one switching at a time, which means that is satisfied in between. If you see, first B is switching, then R, and then Y. But the problem with this end and beginning of this cycle is that at this instant all three are switching together. So to avoid this scenario, we can have, instead of ramp signal, we can have a triangular carrier which is starting and going to 0 after this. So instead of having a ramp which starts at -1 every switching cycle, we can have a triangle which is basically going from -1 to +1 and then coming back to 0. I'm sorry, coming back to -1. So this way what will happen, we will have, let's say you extend the modulating signals for this complete duration. Of course, now we were talking about the switching cycle as this interval, but now our switching cycle will be considered as this. Because one on and off, that is one cycle, correct? So if we draw the gating signals for this now, maybe I'll draw in the same graph. I hope you have noted down this. Now this is the total switching interval, and what will happen, R will remain high up to, sorry, all will remain off during this interval. So it will go down and it will continue with down and then continue as high. So there is no switching happening at the end of the cycle. It is continuing with the on state. Similarly for yellow, that means the Y phase, it will continue positive up to this interval, which is coming over here. The gating signal will go down during this and again it will continue as this. For B, the interval will be little longer, and because we are realizing negative voltage, so off duration will be much longer and then it will be high at the beginning and end of the cycle. So this way what we are doing, we are having only one switching at a time. One converter leg is only switching at a time, or one device is only switching at a time. Understanding my point? Which is why we have triangular carrier instead of the ramp for case of DC to AC converter. And now we can take the name which is famously given to this type of PWM, which is sine triangle PWM. So we have sinusoidal modulating signals getting compared against the triangular carrier. That's why the name comes sine triangle. And this is the reason behind this. We want to have one switching at a time for the converter. Fine. So
Yes,
the output voltages we can write VRO is basically given by, say, MR VDC by 2. So it will be capital M VDC by 2 sine omega t. Average VYO will be given as M VDC by 2 sine omega t minus 2 pi by 3. And VBO given as M VDC by 2 plus 2 pi by 3. So we have balanced three-phase voltages generated from our system on an average basis. Instantaneous values are still plus VDC by 2 or minus VDC by 2. But on an average sense, for each switching interval, we are generating the average value, which is varying in the sinusoidal manner. Correct? So we have understood that with this sine triangle PWM, the maximum voltage what we can generate for the phase, that means the peak phase voltage, is plus VDC by 2. So you can quickly compute that if you have, let us say, 400 volt motor, how much DC bus will be required for your 400 volt line to line RMS. So what will be the DC bus requirement? Can you suggest?
So 326.59.
So that is the peak phase value. What is DC bus?
So 461.88.
Again, Sampan, this is
650,
line to
650,
line
sir.
RMS. Yeah, something around 653 or more.
Yes, sir.
Earlier we had got the number 520 volts when we were running with low switching frequency. Now you see sudden jump in DC bus voltage by 130, 140 volts. So these are some of the design considerations we should have when we are operating our motor from a converter. We need to see that which PWM is operating that. If it is low switching frequency where it can generate a square wave, even 520 volts may be enough for 400 volt motor. But the same converter may not be able to generate full voltage if you start operating with sine triangle PWM. Because the DC bus requirement is now more. It is 653 volts. Understanding my point? Ajay?
Sir, here in when we are using a triangular carrier wave, uh, still there is a point where all the three switches are on.
Where? No, 3 switches can be on. There is no problem. 3 switches on or 3 switches off. That's not the problem. See, if we talk about this instance, all the 3 switches are off. And here all the 3 switches are on. No, after this.
Yes.
The problem is not that. This condition only means that in our converter, let us say I have drawn over here. This condition only means when all 3 are off means all 3 are connected to the negative
Bottom.
DC bus, which means the load is shorted through the negative DC bus. There is no net voltage applied on the machine. Only the currents are circulating within the negative DC bus and the motor. Similarly, if you have condition where all 3 are on, that means all 3 are connected to the top switch. Then the current is circulating within the system and the positive DC bus. There is no net voltage on the machine. So this is not the problem. The problem is when more switches change their position at the same instant. There are more than one switching happening at the same instant. That is the problem. Correct? That may create some EMI issues. So malfunctioning of the converter or something may happen, which is undesirable. Correct? So which is why we need to go for this. And so we have come up with the DC bus voltage requirement for our sine triangle PWM, which is here 653. Same motor, 400 volts line to line RMS you are trying to run. You have now different DC bus requirement for sine triangle PWM. Fine. So I stop the class over here today, and in next class maybe on Tuesday. So we don't have any extra class tomorrow. We'll continue on Tuesday with this further discussions. Any doubts if you have, you may ask quickly. Fine. Manvendra, any doubts?
No, sir.